Okay, so today we get to start our actual real calculus type lecture and topics. We're going to start with the most, well, I don't say the most important thing, but one of the more important things is talking about limits and the derivatives. We're going to start with the limits today. So I'm going to do like I always do. I'm going to go through a couple of slides here. There's a lot of slides here for section 2.1, but I'm going to just go through a handful of them, and then like always I'm going to get right to the homework so you can see some examples. So skip a couple of these preliminary ones. You don't need to know the history and all that. You can look at it if you need. We're going to talk about functions, starting with the functions like this one, which is just a nice straight line, 2x minus 1. Now they're just kind of, it's a little review. They're talking about the different f x equals 2 means f of 2, and then you get a value of 3, and we get 2 comma 3, etc. You know how points are, you know how they work, so probably don't need to go through this. So just explaining what it means when you have an x value and you have the y value. So now we're going to look at this picture, this graph, which is y equals, looks like it's 2x, sorry, looks like it's a negative 1/2 x plus 2. Maybe it's just a random graph here. Yeah, they want you to find some of these here. Let's go to this one, 2x minus 1. Okay, so in this particular case, they want to know what domain value is near 1. They want to figure out what's going on here as you get closer to 2. So that's what a limit is all about, is you're looking at a function, and the question is, as the x value gets closer to a certain number, some random x value, like in this case x equals 2, the real question is what's happening to the y value? What's the pattern? So here's what I mean. Look at this table. 2 right here in the middle. This is what we're trying to figure out. We're trying to figure out what's the behavior as you get closer and closer to 2. So as your x comes in from the left toward 2 and it comes in from the right, all converging at 2 right there, the question is, what's happening with the y values? So you see here, going by this equation here, if you start plugging in 1.5, you get 2. You plug in 1.9, all that. The idea here in the beginning is plug in numbers as close as you can to the number 2 from the left side. So 1.9, 1.99, 1.999, you can get as close as you could possibly get to. You know, 1 point, and put 8 nines in there. And then at the same time, you're coming from the other side, you're getting closer and closer. You try 2.1, 2.01, 2.001, and you're getting closer and closer to 2 without actually touching the 2. Okay, kind of like an asymptote. So then they want you to see, when you plug in all these, you get all these y values here, and your idea is to try to figure out a pattern. So from the left side, you can see it looks like it's approaching the number 3. And from the right side, it also looks like it's approaching the number 3. So as long as these are the same number, that's one of the keys to limits, then you'll be able to know that the limit is going to be 3. And that's the question you're always going to be asking yourself, is as you get closer and closer to a certain x value. Now this x value, by the way, is going to be given to you. They're going to tell you, here's a function, find us the limit as x gets closer to a certain number. In this case, as you get closer to 2, what happens to the y? That's what they're asking you. What y value are we getting closer to? And in this case, the answer is 3. Okay, so on this one, we're going to have another function, discuss the behavior of the values of f of x. Now remember, that's the y value. What's happening to the y value when x is getting closer and closer to 2? So in this case, you don't have to graph every time, but the graph is going to help us out. You see this big fat 2 they put right here. They want to know, as you come in from the left side, what's happening to the y value. So you see here, look at all these points. As these are getting closer and closer to the number 2, what's happening with the y value right here? What is it doing? And you can see where it's getting closer to. And then at the same time, when you're coming in from the higher x values, you're getting all these points over here. What are they approaching? What point are you converging to? And that's the question right there. That's the limit we're trying to find. What's the y value? So you see, let me put it on my screen here. from this picture they have, they're just talking about all the different activity that's happening. Okay, you see those red lines? Those are all the x values as you get closer and closer to 2. That was our given again. Remember, they're asking what's the limit as x approaches 2. So then the question is, okay, my answer is what y values are we getting closer to? So you look at all these different x's and you bounce it up against the line. That's going to tell you the point, which is going to tell you the y values. And what's the y values? What's the behavior doing? And it's approaching that y value of 4. That's the question here, is what is the limit? What is the graph approaching as we get closer and closer? And you see it's getting, the y value is getting closer to 4. So always remember, when they ask us to find a limit, they're asking for a y value. I cannot say that enough, because there's a lot of things, you're going to get a lot of notation, a lot of stuff is happening on the screen soon. And it's going to be hard to understand what in the world they want, especially from this graph right here. They're always asking, what's the y value? What are we getting toward? Okay, so the symbol, how you write this, by the way, they're going to be asking for what's the limit, this LIM, as x approaches 2 of the function. Now, sometimes they're going to say, what's the limit as x approaches 2? And they'll give you the actual function, like x plus 2, like that. Okay, either way, these are asking the same thing if they've defined the function up there. Okay, but that's what they're asking. So in both cases, same thing. They're saying x is approaching 2. What is y approaching then at that 2? That's the question at hand for each of these. So this is the notation you're going to use. One of these two. And you see here on this slide, they're just telling you the limit of the function as x approaches 2. Okay, or you could say the limit as x approaches 2 of the function. Either way, it's the same thing, and the answer is 4. Okay, and be careful, it's not LIM as y approaches 4, something like that. Not that. You just say the limit equals 4, or in this case, that limit right there equals that 4. That's how you're going to write the notation on each of these. Okay. So, if you look at it, a lot of you notice it's like, well, why do we have to go through all this process? I could just plug in f of 2. And when you plug in f of 2 into this function right here, you get 2 plus 2, you get a 4. You get the same answer without doing all these decimals. And that's how it's going to be at the beginning, okay, where the limit is basically what the function is. In fact, that's how I'm going to have you solve these, is when you try to find the limit, go plug in that x equals 2 into the function, see what you get. But most of the time, the limit's going to matter where you have problems where there's a gap, there's a hole, there's an asymptote. A lot of times the limit does not exist, or sorry, the graph does not exist there, so we're going to have to deal with it. Okay, so a couple things here, little things that we're talking about here. Just talking about how it is. The capital L is usually what represents the limit, the answer that we're talking about. And here's a key right here. I'll kind of reinforce what I was saying. Okay, the function is approaching an L. The y value is approaching that L as the x is approaching some given number, C in this case. X approaches C. Okay. So now we have one of our piecewise graphs. You remember this from before. This is just the absolute value. And to kind of refresh your memory, you know what the absolute value looks like. Remember, it's the V-shaped. So what they're saying in this case is it's equal to the function y equals x when x is positive, and then when x is negative, it's y equals negative x. It's just another way to write the absolute value function. Okay, so what they're going to look at is they want to know what is this right here. Okay, this function, absolute value over x. Okay, so just look at this function. This is what we care about. They want to know what is the limit of that function as x approaches 0. That's the question they're asking. They want to know, what kind of y value do we get? Okay, so this is only the absolute value function. But here's the trick. Here's what we have to do for this h of x right here. We need to get, and I'm going to go make a table up here. Okay, for the h of x, we need to make a table to see what happens. Because we want to see the behavior. Now remember, our question is, what's it going to be at 0? Okay, it's supposed to be a question mark. So let me just tell you, the first trick, it doesn't always mean it's your answer, but go ahead and plug in this 0 and see what you get. And you're going to see this is undefined. Remember, you can't divide by 0. This is why we want to know the limit. It doesn't exist, but we want to have an idea of what it is. Can we somehow figure it out? So this is where the limit comes in. We don't know what that is, so the answer is, let's try numbers really close. This is how you're going to do these in the beginning. Go plug in numbers really close to the 0 and see what the pattern is. See what's going on here. Okay, so I'm going to keep erasing and all this down here just as like my little scratch pad. So let's plug in the first one, which is 0.5. Now remember, what we care about is as we get really close to 0. And you're going to see 0.5, absolute value of 0.5 is 0.5. We get a 1 right there. Okay, hopefully that is okay for you all. Now, again, we take the absolute value, which just leaves it as a positive. Let's go do it for 0.1. You notice we get the absolute value of 0.1 all over 0.1. And that's 0.1 over 0.1, and you see it's a 1. And you're not doing this wrong. If this is what you're getting, this is the answer. So last, I'm going to do it for, 0.01. And it is going to require a little bit of writing out, a little bit of work on each of these. Okay, you see? Looks like we're approaching 1. You see, as I get closer and closer, nothing's going to change here. It's always 1, 1, 1 every time, so no difference. Okay, however, let's start looking at it from the opposite side. Negative 0.5, negative 0.1, negative 0.01. And I'm going to try to do this just to save a little bit of time for us, but let's see how it goes. So when I plug in negative 0.5, I get an absolute value of negative 0.5 on top over negative 0.5. So this becomes a positive 0.5 on top and a negative 0.5 on the bottom. And we get a negative 1 right there. It's going to be pretty much the same thing over here. Let me see if I can just kind of shorten this work up for you. If this is a negative, that's going to be a negative, that's going to be a negative. And like before, the top is going to come out to be positive 0.1 because the absolute value eats up that negative, but the bottom, it stays there. So we end up with, again, a negative 1. And you can see over here when I plug in a negative 0.01, you see, and the whole game is try to get the pattern of what's happening, and sure enough, that's also negative 1. So in this case, in that last example with the x equals 2, and we were plugging in the different numbers, and we saw it was going closer and closer to 3, we saw a clear pattern of the limit was 3. But in this case, notice here from the top, it's approaching 1. Here from the other side, it's approaching negative 1. They have to be approaching the same number. That's the core definition of a limit, is when you come in from both sides. So you'll learn here, this means the limit doesn't exist. It just means we don't have the same thing from both sides. And that's the key to limits. You have to check it from both sides. You can't just do like a lot of students will do. They'll plug in the 0.5, 0.1, 0.01, and they say, oh yeah, it's going to 1, there's my limit. That is the limit from one side, but it's not the limit from the other. And that's what this is going to be. We're going to talk about limits from both directions. So, look at this next slide here. The limit from the left. Okay, so when we go from the left, it's this little negative right here. Now you see that negative? It might be hard to see, but there's a little negative after the C right there. The limit, let's pick an example. As x approaches 2 of some function, that little negative that looks like it's a power, that means it's from the left. If I give you the limit as x approaches 2 with a plus right there of the function, this is going to be from the right. Okay, so if you look at the example that I did and the one earlier, we were finding the limit from both sides. Sometimes they're going to ask you just to find one. Okay, what's going to be happening from one side or the other? Okay, if no direction is given, if you don't see that little plus or minus at the top there, then it's known as the regular limit and it's a two-sided. You got to go find it from both directions. So if you see the little minus, just find the limit from the left. If you find, if you see the little plus up there, that means go find it from the right. If you don't see it at all, any of those, you have to go find both. Okay? So just to kind of show you what I mean here. When I go back to that table, if we were to find the limit, and I'll get to this notation in a second, the limit as x approaches 3 from the left side of a function, that means, again, you can't find, assuming that you can't find 3, like it doesn't exist. I want to get numbers from the left side leading up. So think of a number line, 2.5, 2.9, 2.99. That's going to be from the left side. Think of a number line. If I'm asking for the limit of a function on numbers from the right, that little plus there, then I'm looking for the 3.5, the 3.1, the 3.01. This is going to be the stuff from the right, and we're going to see what's the pattern. What's the pattern right there? That's what they're looking for. Okay? So that's when they say a one-sided limit, they're looking for that plus or minus, and they want to know what you get. Now on this slide here, you see the limit with no little plus or minus is going to check from both sides. It's only going to exist if you check the left and you check the right and they're the same. If they're the same, then that's what the limit is going to be. It's got to be the same. So in this particular case, remember from the left side, we checked it, that table that I wrote a couple slides ago. From the left side, we found that it approaches -1. From the right side, it approaches +1. These two numbers are not the same, therefore the limit does not exist. The limit with, without the plus or minus, this regular limit, I call it the regular limit, the two-sided limit. So whenever you're checking for a limit, the rule always is check from the left, check from the right. If they are the same, that is your limit. If they are anything different, then the limit does not exist of your graph. Okay? So now we're going to use the graph to get the behavior as a graph approaches -1. Okay, so you look at our graph. -1 is right here. So we want to know the behavior of the graph. Well, remember, this is coming in from the left. And you see what's happening to the y values right here. Here's coming in from the right. Look what happens to these y values. If they're what we call converging, if they're meeting at a single y value, then that's their limit. In this particular case, both sides, from the left and the right, they're approaching the y value of +1. That's why we have a limit of +1. Sorry. Okay, they're equal and they agree, therefore the limit is going to be positive 1. Okay, and the way to look at it on a graph is just look at both sides. This chunk of the graph on the left of where we're looking for the limit, and this chunk of the graph to the right, are they meeting at the same spot? Now, the dot doesn't have to be there. They just have to meet at the same spot. They have to be pointing toward the same spot for the limit to exist. Okay, now we want to discuss the behavior going toward positive 1. And this is the one that really does get a lot of people, confuses people at times. So, remember, we want to know what's the limit as x approaches 1. Limit of the function as x approaches 1. So, here's 1. Look at your graph leading up to 1. And it looks like from the left side, x approaches 1 from the left. That's what that negative means. Remember, it doesn't mean negative 1. It means the left side of positive 1. It looks like it's approaching the value of 3. It's getting higher and higher and higher, and it's approaching 3. Now we look at our graph from the right side, and you see my limit from the right side of 1. This also appears to be approaching 3. Therefore, because these are both the same, then we know the limit as x approaches 1 with no side defined is going to be 3. Now, a lot of you are looking and saying, well, how can that be? Because the point doesn't exist. There's a big hole right there. And it is correct that there is no y value at 3, but that's not what a limit is asking. The limit is asking, are the two sides of the graph approaching the same number? Are they coming to the same number? We don't care if they actually hit 3. It's, are we getting closer and closer and closer to 3 as we get closer to the x value of 1? That's the question that's being asked here. So the limit in this particular case is 3 because when you check it from both sides, you're getting that answer. So again, I know these pictures are not always clear. That's why I try to write them a different way, but you see this picture as I clear out the stuff here. They're showing you that as my x value gets closer and closer to 1 from both sides, the y values from both sides are approaching 3. That's our limit. The left hand and the right hand limits are equal. Therefore, our limit is 3. Okay, now, f of 1, this is, to be clear, we're not asking, go back. Not asking, when I say f of 1, limit as f of 1 approaches 1, f of x approaches 1 is 3. That's what we're getting close to. F of 1 is just saying, what's the y value? What happens when you plug it in? Well, if you look at the graph, 1, there is a hole right there. There is no point at that value. But there's two different things. The limit right here, as f of x as x approaches 1, that exists. That's 3. Here, f of 1 does not exist. So two different things they're asking. And now your last part of this example, you can see we're looking for what happens to the graph as we approach 2. So looking at 2 right here, I'm gonna go a little backwards first, and I'm just gonna say, what's f of 2? Okay, not the limit, just what is f of 2. So if you look right here, where does the graph have a point when x equals 2? And you can see it's not up here at the top because there's a hole here. Right there, f of 2 is that circle at 2. Okay, that's the point. So if they're asking for the point, the y value, the answer is 2. But in our case, we're going to talk limits. Okay, so you look at it. When we come in from the left, okay, as we get 1.5, 1.9, 1.99, you see what's happening right here. We're following the function. We're approaching the y value of 2. So from the left side, the limit is 2. But as we come in from the right side and you look at the function, that's always what it is, looking at the function, here it looks like it's approaching 5. So this is a case where you have two different sides, two different limits. From the left, again, as x comes in from the left, the y value is approaching 2. That's why they say this right here. But from the right side, the limit is 5 because the y value is approaching 5. So look at the different y values. What are they getting to? If you were to plug these in, you'd get 4.5, 4.9, 4.99, 4.999, and you see a clear pattern that it's approaching 5, but if you look over here, it's a clear pattern that you're approaching the 2's. So, because from the left side and from the right side, because these two values right here are not the same, they have to agree, therefore the regular limit does not exist. Okay, and it's all because of that. Because of the fact that they're not pointing to the same spot, we don't have a limit. Now keep in mind, you got to make this two distinctions. The point exists. We talked about that already. It's f of 2 equals 2. There is a y value there. It's 2. But because it's coming in from two different directions, you're not going to the same spot. You're converging. The limit does not exist. Okay, so an easy way to tell is if they're connected. Like right here, the limit exists. If it's continuous like this, the limit exists. If it's broken, then it does not exist. Okay? It's okay if it has a hole because it's the same connection from both sides. Holes are okay in this for limits, but big gaps right here, that's when you don't get a limit. That's when the limit fails to exist because you're not converging. You're not meeting in the middle. Okay? Again, you look at the hole, they're aiming for the same spot. It may be a dead spot, maybe an empty spot, but they're aiming at the same spot. That's the difference. Limit exists here. Only place on this graph the limit doesn't exist is when it jumps, like it scoots upward. Okay, and that's what we're talking about. Okay, so a couple properties here. If we have two different functions that have two different limits, this L and this M, this f of x and g of x now. Okay, we've got two different functions and they both have a limit. So the limits exist, we're just assuming this. Then there's some properties we get here that says if you're having a constant function, remember like y equals 3 or y equals 9, if k is a constant, it doesn't matter what x is approaching, the constant is going to be my limit. It's going to approach itself. Okay? If you have y equals x. Now remember, when you see this right here, this is the function. It's like the equation y equals x. So if you ever get it equal to itself like there, then it's just the limit is whatever the limit is whatever x is approaching. Okay, now it gets more interesting. These are the ones that matter. If you have two functions that you're adding together, and you can find the limit of each, like in this case, we know the limit of the first one is L, the limit of the second one is M. If you know each individual limit and you're adding the functions, you can simply add the limits. And this is going to work again. When you subtract two functions, you can just subtract their corresponding limits. If you have a number multiplying in front of a function, like this, you can just find the limit of the function and then multiply the answer by that k. If you're multiplying two functions together, you can multiply the two limits. If you're dividing two functions, you can divide the limits provided that this bottom one does not approach 0, which kind of makes sense. And the last one, if you have any kind of a root, you can find the limit of the function itself, get the limit, and then take that same root of the answer, and you'll get it. And again, the caveat is as long as you don't have a square root of a negative number or a fourth root of a negative number. Okay? All right, so now we're going to get to some examples here. And you see them working these out, and I'm going to go through this a little bit faster because I'm going to explain them more when we do the actual homework problems here. But in the first one, okay, this is the problem, so you know, because this looks kind of convoluted here. That's what they're asking us. The limit of the function x squared minus 3x as x approaches 2. Well, in this case, they did the breakup where they just said, let's go find the limit of x squared, and we'll subtract the limit of 3x. And it doesn't have to be this way, but just to show you, this is a regular function right here, x squared. So when you plug in the 2, you're going to get an answer right there. You're going to get the 4, and you can solve with that. Then you plug in the 2 in this other one, you're going to get a 6, and we can just subtract those two. Okay, so you could have also done the same thing. I'm going to tell you right here. In each of these, if you break this down a little bit more, that right there, remember, they said it for a root, but I'll tell you right now, if you have a graph like that, that's continuous, no gaps, no jumps, nothing like that, then you can simply just go plug in the x to that function right there and get the 4. That's how they did that. Just like this one, it was like that function y equals x. The answer was just 2. You can just plug them right in there and you're going to get a nice easy answer. In these beginning ones, when I have this limit of x approaches 2 of x squared minus 3x, I'm simply going to start by plugging in the 2 just to see what we get. Now, like I said, in time, minus 3 times 2, we get this negative 2. That's our limit. That is the value. That is the value of the graph. That is the value of the limit. As we do more and more of these, you're going to get functions where it no longer exists. You're going to get these complicated ones where it's ugly and there's no answer. In the beginning, though, yes, it's going to be as simple as you just plugging in the numbers. Okay? But you'll see what I mean in a bit, where there's going to be these functions where nothing is working, nothing is, existing. We're going to have to try out some more. So in this one, it's the same thing. The second one, they find the limit, they plug in 4 into both of these. So when you take the 2x function, you think about that, you know how a y equals 2x function looks like this. So if you know there's no gaps, breaks, or it's a normal, I'll call it a regular function that we've had before, just plug in the number and you get the 8. Here on the bottom, same thing. It's a 3x plus 1. It's a function that looks like even more up, maybe more like that. But either way, they're both continuous and they both continue on forever. So just plug them in and that is our limit. Okay, the point exists. That is the answer on each of these two problems. Okay, but our next example is not always going to be the same. Okay, so a couple more ideas. We have a theorem here. So if you plug this in, any polynomial function. Okay, in this slide, I got to tell you, probably should have come before the ones we just did because we had the polynomial functions just now. But if you got any polynomial where it's just regular powers of x, power 1, 2, 3, 4, 5, 6, 7, all the way up forever, all those polynomials we spent time talking about, then you just plug in the number. You just literally plug in the number for c and you get the answer. Okay? If it's a rational function, all right, that's a key. As long as the denominator is not a 0, you can just go plug it in as well. All right, so that does make it easy, and that's what I was talking about. Just plug the numbers in. So here you see it. It's a regular polynomial. We just plug in the 2 into each x, and it's like we're finding the y value. We get 21. That is the limit. On part B, okay, it's a root, but a root's going to be as fine, especially when it's an odd-powered root. If it was a square root, we got to watch out for a negative, but when it's an odd power, we're good. Plug in the 1 in each of these, and simplify the root, we get a 0. That is our limit. That's where we're going. Okay, so yeah, this slide's a little bit backwards. Sorry about that. All right. Now, we get to a little more complicated stuff, but not much here. In this case, we have a regular polynomial on top. We have a regular polynomial on the bottom, which means to find the limit as x approaches 2, just replace every x with 2. And as long as we don't get a 0 on the bottom, which we don't. You see here we get a 7/8. That is our limit. That is the answer. Here, same kind of thing. We've already dealt with this problem, but we have to mainly worry for a rational function. Just don't give me a 0 on the bottom. So you plug in the 4, you plug in the 4 again, and you get just plain 4 over 4. You get a 1. That's our limit. Okay, now we get to things a little bit more complicated here. All right, these are the piecewise graphs. So if it was a plain polynomial, then you have the answer. But when it gets to be something like this, then we start talking differently. So we want to know what's the limit of this function as x approaches 2, and that little negative again means coming from the left side. So that means when you plug in numbers, you want to make sure you pick the graph that talks about the left side of 2. That's these x values, all less than 2, 1.5, 1.9, 1.99. So I'm not making you plug in the numbers, but if you were, you would see you'd be approaching the answer of 5. Okay? Plug it into that first one. From the left side, it gets closer and closer. The y value, I should say, gets closer and closer to 5. Next, we're going to plug it in from the right side, that plus. So we're going to choose the second function where x is greater than 2 because we're coming in from numbers that are bigger than 2. Then you plug 2 into this function and you see you get 2 minus 1, you get a 1. That's again our proof. If they do not exist, if they're not the same, then this limit here will not exist. One-sided limits, they have to be equal for the main limit to exist. If they don't, then there is no limit. And then last part, because the definition of a function does not assign a value to x equals 2, then f of 2 also does not exist. Okay, because notice neither of these had the equal sign on the bottom, therefore there is no defined place to plug in f of 2. So again, I'm going to keep pointing out, they keep showing this in the slides. We're going to find f of 2 and we're going to find the limit as x approaches 2. Sometimes one of them exists, sometimes the other doesn't, sometimes they both exist, sometimes neither of them exist. Sometimes they both exist and they're different. They really have, I'm going to say, they don't have anything to do with each other all the time. Okay? Now, our last part here, which is not going to be so necessary today, we're going to get into these a little more later on in the book, but we talk about an indeterminate form, okay, when we get this 0 over 0, which is going to happen a lot, okay, because later on we'll find, and let me go back a few slides and show you, remember that theorem when there's a 0 on the bottom? Okay, so as long as you don't have a 0 on the bottom, you're going to have a limit. We are going to have cases where we're going to get a 0 on the bottom, and we're going to talk about those limits. But we're also going to have cases when we have a 0 on the top and the bottom, and that's what we call an indeterminate form. We just can't tell what's going on with it. We need to do more work is what it's coming down to say. So here's a case. We have x approaches 2 of the function x squared minus 4 over x minus 2. If you plug in a 2, okay, right here into the original. Now, I wish they weren't showing all this because they're kind of ruining the surprise. But if you were to plug 2 into that one, you see you get a 0 over a 0. And that tells us nothing about our limit. However, if you were to break down the top and the bottom, you factor them. Remember, factor the top, factor the bottom. If you have an identical factor, now you just have this. And now if you plug in 2, magically you get a 4. That is your limit. Okay? What happened is, this part here made it happen that 2 won't work. We can't plug in 2 to the problem. But if you also get a 0 on the top, there's a very good chance that the 2 factors that are causing the 0, this x minus 2, they may cancel themselves off. It means that the point does not exist. There's still nothing there, but this means because of this cancellation, it allows you to find your limit, and it tells you there's going to be a little hole in the graph. Literally at the point 2, 4, there's going to be a hole. So maybe the graph does this and it does that. There's a hole there. Okay? That's what's happening. The functions are not exactly the same, but the limits are the same. That's the key. If you can simplify a function, it may be different than the original function, graph-wise, but the limits don't change. So, if we have a limit doesn't equal 0, and then we have another function, the limit does equal 0, then that's a case where it doesn't exist. So if there's only a 0 on the bottom but not a 0 on the top, that's when they mean it doesn't exist. If there's a 0 on the top and the bottom, check your problem because you might be able to factor and cancel. That's what they're trying to get at with that one. So here, same kind of thing. Determine if the limit is an indeterminate form. Find the limit or explain why it doesn't exist. So plug in the 2. You get a 0 on the top, and it looks like I get an 8 on the bottom. So remember, if there's a 0 on the bottom, we have a problem. If there's a 0 and a 0, then we have an indeterminate form and see if something cancels. If you get a 0 on the top and a 0 and a number on the bottom, that just means 0. That is your limit right there. It's not an indeterminate form. And in fact, it's just a 0. Now they wrote this wrong. That should be a 0 over 8. Little math error on their end. But same thing. We get 0 over number. We get a 0. So the limit can be 0. That's all it's saying is in my graph, we're getting, as we get closer and closer to 2, we get closer and closer to the y value of 0. Don't forget the first thing we talked about here. Now, same thing in this problem. We plug in a 2. This is kind of like the one before. If you plug in a 2 right now, you see on the top you get a 0, and on the bottom you get a 0. So that means go factor. So we have the same exact limit here. On the top we have an x minus 2. On the bottom we have an x plus 2 and an x minus 2. These cancel. And now our limits, as still x approaching 2, we just have a 1 on top and we have an x plus 2 on the bottom. Now plug in the numbers and you see how we get a 1/4. Okay? That's what we're doing whenever we have these problems. We want to just plug in the number and see what you get first. If you get something weird like a 0/0, you have to do what I just did. If you get a 0 only on the bottom, you can stop right there and just say, hey, this limit is not going to exist. If you get the 0/0, you factor, like we did right here. And like the last example, remember, if you get a 0 on the top, then the limit is actually the number 0. The y value is approaching 0. So, kind of a summary of what we just did. I didn't need to write all that just to show you. We get our 1/4. Okay, here, same kind of thing. We're trying to explain, does the limit exist or not? Plug in the 2. Looks like I get a 4 on the top. I get a 0 on the bottom. So therefore, this is not an indeterminate form, so we don't even have to bother factoring. You can, but what's going to happen is you're still going to get the same thing. A limit does not exist. Okay, our last part. This is what's going to become the key to the next section, that difference quotient. We talked about this a little bit before, but I'll remind you right now. This is that you have some function, you have an open interval containing this number a. So what we're going to do is we're going to find the limit as h approaches 0. We plug in a plus h to the beginning. We just plug in f of a to the other, the function. We subtract them, we divide by h, and we try to see what happens. Now, I'll do it here, or I'll show you this one on this example. On this example right here, what they want us to do. So we want to find out this whole box, what this is. So the first thing is just regular plugging in an a right there is 2a minus 3. That's easy. Plugging in f of a plus h is going to take a little more work. And remember, everywhere you see an x, you replace it with this a plus h. So I'm going to rewrite the limit as h approaches 0. In place of this right here, I'm putting this. So it's a 2a plus a 2h plus a 3. That entire thing I just circled right here is replacing this. Then we're subtracting this function, 2a minus 3, and all of that is over h. And now I simplify. So on the top, I have a 2a plus a 2h plus a 3 minus a 2a plus a 3. Oh, sorry. Let me go back and fix. I messed up right here. That's supposed to be a minus 3. From the original function, that's supposed to be a minus. Both of those. Okay, now we have it right. And now we just keep simplifying. H is still approaching 0. And now these 2a and negative 2a cancel. The 3 and the negative 3 cancel. I have a 2h over h. And now the h's cancel. And now I just have the limit as h approaches 0 of 2. Remember, if you have a constant function, your answer is that right there. Okay, that's our answer to the problem. So I'll stop there. I'll get to some problems right now. Let's get rid of the lecture part and let's just I'll show you some of your homework examples like I always do for a handful of them. Okay, so here's your homework, your assignments. I'll just pick right up with this 23 and see what this is all about. Okay, so now it's one of those where they give us the graph. Use the graph to estimate the function value at f of -5. So some of these in the beginning are just going to kind of make sure you understand how this works. So let me zoom in on the graph. So here at -0.5, they're wondering right here, what is the value of the graph? Well, I can look up here and I can see very clearly, it looks like a 1, so that's my 1. Excuse me. Okay, and that's all they wanted on that one. Just look at the graph and come up with the picture. Now, jump through a few more, and that's all these first. You see as I scroll through these, they're just all kind of asking the same kind of thing, just identify from the graph. If I was to look at, let me just look at this one here, at 4, and this is an important one. Forget about what they're asking here. If I just want to show you the graph here. If I said, what's f of 4? Okay, here's 4 right here. What's f of 4? I'm just asking you a different random question. Remember, where does the graph exist at 4? It's right here. F of 4 equals 2. If I asked you what's the limit as x approaches 4 from the left, then I would tell you limit as x approaches 4 from the left side of the function. Then it's 0 because that's the y value that it's approaching right here. If I said, what's the limit as x approaches 4 from the right side? From here, it's also approaching 0. They're approaching the same one, therefore the limit as x approaches 4 is also 0. Okay, just an example of the kind of things they're going to ask you. What's the function, or what is the actual piece? Either or. They're going to ask you what's the value of the function, or what's the, what is the limit approaching. So you have to look at each problem individually. See, what are they asking here? Okay, on number 27, same kind of thing here. They tell you we have a bunch of parts. So on part 1, they're asking find the limit as x approaches -2 from the left. Okay, so now let's look at this one. First, identify -2. They're not asking what's the value of -2. If they were asking the value of -2, I'll tell you the answer. It's going to be where that dot is at -2. Right there. That's the value of f of -2. But what they're asking for is, what's this coming from the left side? What y value is that? So you can look at it. Looks like it's approaching, as x approaches -2 from the left. So you're coming in from the left side of your graph. This is my target. What y value is that? Not does it exist, but it is there. That open circle looks like it's at -2. That's our first answer. Okay, now the second question is, what's it approaching -2 from the right side? It's the same kind of thing. Let me pull up this picture a little bit larger. Okay, so here's my -2 right here. This time we're coming in from the right side, right here. Follow the graph. I don't care about this. I don't care about this. I'm just looking at the closest place. Remember, we want to get as close as we can. And what is that approaching? Well, that looks like it's also approaching -2. Good. So now part C is, what's the limit itself? No direction. X approaching -2 of the function. Well, we've already found -2 from the left. We've found -2 from the right, which is what you'll do every time you're finding a limit. If they're the same, which they are, the limit exists, and that is the limit right there. From both sides, it's coming to the same spot. Okay, and then over here, what is f of -2? Well, remember, that's now asking what's the coordinate. That's it right there. That's 0. That's the y value. That's it for that one. Now, before I go on to the next question, I just want to, we kind of got an easy one on that one, but let me ask the same question. Okay, looking at this graph, let's make this bigger. If they said, what's the limit as x approaches 1 of the function? Okay, so looking at my function here, here's 1 right here. Okay, so if I want to know what's the function of, what's the limit as x approaches 1 of the function, we have to check the function on the left side, and it looks like from the left side it's approaching 3, and from the right side it's approaching -3. So from the left the limit is approaching 3. From the right it's approaching -3. Because they're not the same, this limit does not exist right here. Remember, they got to meet somewhere. Whether they meet at a hole or an actual dot, it doesn't matter. There just can't be a gap. They can't be meeting at different numbers. That's the idea here when we talk about a limit existing or not. Okay, let's look at number 31. Okay, on this one, we have a given limit. They want us to find the given limit here. So we have the limit as x approaches -9 of x squared minus 6 over 9 minus x. Now remember, these are both polynomials, so they're they're no big deal. There's nothing special about them. Just plug in the numbers and see what you get. So I get an 81 minus 6 on top. On the bottom, I get a 9 plus 9, because that's a -9 minus a -9. So I get a 75 over 18. No zeros, therefore this is my limit, and the only thing I have to do is maybe simplify this a little bit. 25 over 6, and I do say simplify your answer. So 25 over 6, hope I simplified that right, and that's it. Okay, hopefully that is not too bad. And remember the rules. If there's a 0 on the bottom, it probably doesn't exist unless you have a 0 on the top. You got to check both. Do you get a 0 over 0? If so, that means go factor and then plug the number in again. Do you get a number over 0? If you get that, you don't have to do anything. Just end the problem and you're done there. Okay, if you get a 0 on the top, the answer is just plain 0. Now they want us to sketch a possible graph of the function that satisfies the conditions below. So f of 0 is 0, which means we're going to have a point at the origin. Try to draw that. But as you come in, the limit of the function as you approach 0 from the left is going to be 3, and if you approach it from the right, it's going to be 0. So it's going to look something like this. From the right, it's going to be approaching 0, and I just made that on purpose. But from the left, it's going to do something that approaches 3, kind of like that. That's what they mean by approaching different spots. So from the left side approaching 0, we're going to get a function of, the function will be the y value over 3. Approaching from the right, it'll be a y value of 0. So let's look at each of these. So first off, we have the point 0, 0. Okay. From the left side, it looks like the limit is 0, and that's not what they said. They said from the left side, the limit is 3, so that's not the correct one. And here, from the right side is 3. They have them backwards, so not A. B looks a little better. We have the 0, 0. From the left, we're approaching 3. We're approaching the y value of 3. From the right, we're approaching the y value of 0. That one looks good. This is probably going to be my answer. But like always, I want to check all these. Okay, here, approaching 0 from the left, y value of 0, so no good. Approaching a y value of 3 from the left, or from the right, not the right one. And that other point didn't exist. Now the tricky one is D here. Okay, from the left, it is approaching the y value of 3. That's confirmed. From the right, it's approaching a y value of 0. That's confirmed. But look at where the dot is. F of 0 is at 3. Everything is right on this last one except this one that I have circled. That's our mistake. So our answer is B, I believe, and we're good here with number 35. Okay, so let's look at number 39. Make sure we're still doing something out of 2.1 here. So in this particular one, they give you a function, f of x equals absolute value of x minus 11 all over x minus 11. And the first question they ask is, what happens when you're coming in from the right side? F approaching 11 from the right side. So here's what you can do. What I'm going to do is I'm going to just go find the 11.5, find the 11.1, numbers as we get really close. And you'll see we can do this not too bad. When you plug in 11.5 in the absolute value, you get a 0.5. Absolute value is 0.5. We get a 0.5 over 0.5. This is a 1. When I plug in 11.1, we get a 0.1 over a 0.1. We get a 1. So coming in from the right side, we're getting a value of 1. That looks good. Okay? But coming in from the left side, now I'm going to plug in something like 10.5 and maybe 10.9. Again, remember, from the left side, coming up to 11, picking numbers as close as I can get. Maybe 10.99 is even better. But when I plug in 10.5, we get a negative 0.5 in the absolute value divided by a negative 0.5. So what happens is the top becomes a positive, the bottom stays negative. We're getting a negative 1 right here. And to save us the work, we're also getting a negative 1 down here. So from the left, we had this kind of earlier, we're going to negative 1. And of course, the grand question is, without a sided, this is the right-sided limit, part A, part B is the left-sided. This is a double-sided when there's nothing. When there's nothing, that means do them both. The rule is, are they the same? If they're not, the limit does not exist. And the last part is, go find f of 11. So we plug in an 11 here, f of 11, and you'll see what happens. On the top we get a 0, on the bottom we get a 0. If it was a limit, we would try to simplify a factor. But remember, we're not talking a limit here. This is actually go find f of 11. That gives the absolute value over 0. That's 0 over 0. This thing does not exist. There is no dot. There's a big hole right there. So that's it for number 39. Okay, let's look at maybe one more of these, I think. Number 43, yeah, we're still in section 2.1. So on this one, if the statement is always true, explain why. If it's not, give a counterexample. If it's a polynomial, go back. This is the actual thing they're trying to state here. So the first line was the instruction. The second line is the statement that we're trying to say it's always true, or if it's not, let's show an example. Now, when you start getting theorems or statements like this, I'll just kind of give you a quick lesson on logic. If I tell you something always is true, it's easier to prove somebody wrong because you just have to find one case where that's not true. Okay, so if someone makes a statement, this is always true, find me one example where it's not, and then you're done. If you can't, then it's probably going to be true, and you have to sort of explain it here. So they say if f is a polynomial, then as x approaches 0, the right-hand limit exists and is equal to the left-hand limit. So you think about that. We talked about with the polynomials, because a polynomial has no gaps or breaks, they're continuous. Therefore, you're always going to get the same thing. Okay, from the left and the right, it's always going to be basically equal to what f of that point is. So, and again, these are not the nicest problems, but I don't think it's false, so I'm not going to say not always true. I think it could be this one or it could be this one. Now let's look at the two explanations. So if it's a polynomial, right here they tell you that the limit is actually plugging in the f of c. Okay, so therefore you get the two sides equal, and it sounds like that one looks good. In the second one, they tell you the same thing. X versus right hand limit is always equal to left hand limit. I'm trying to see what the distinction is between these two. What am I missing? Oh, okay. This is it's really minor right there. All right. So you had a theorem earlier that said if it's a polynomial, the limit is simply f of whatever that number is you're approaching. Here, it's not the actual number. It's not the x you're approaching. That's the one little flaw right there. It's a minor mistake. So that's it on that one. Sometimes these problems look a lot more difficult because of the wording, because so much is going on. But read part C again, pause it if you need, and kind of look at it. Essentially, the limit exists because in a polynomial, the limit is the point, the y value, when you plug in C. And then if the limit exists, then you know the left-hand limit and the right-hand limit have to be equal to each other and that limit right there. Okay, so yeah, at this point now we're at 2.2. So I'll record another video on that next time, so you can kind of see that one here. But that's it for today's on this one. So 2.1, you should be good to go. You should be able to do, we're all the way through 43, so these all the way up to the mid-40s you should be able to do, knowing section 1.6 and 2.2. I'll record something today or tomorrow for 2.2, and that should wrap up all your work for chapter 3. So until then, have a good one, and like always, ask me if you have any questions, shoot me an email. Take care.